Hello all. You as we discussed, like some student asked me to make audio PPT on this vector insert DNA ratios, how we calculate vector insert DNA ratios for ligation reaction, and we'll see that what is the formula, how we put the values in that formula, and how we calculate it. So generally, like what I want to add initially is that vector is to insert, or some type people write insert is to vector ratio. So you have to be very careful while writing the values, or while you see the formula. So you have to be very careful what people are using. Vector is to insert, or insert is to vector. Generally, it is insert is to vector by in formula. So you have to be careful in that, and we will also talk about that why people keep insert more than a vector. So we'll talk about that also. So now, to test various vector is to insert DNA ratios to determine the optimal ratio for a particular vector and insert. In most cases, a 1 is to 1 or 1 is to 3 molar ratio of vector to insert works well, but you may want to consider 1 is to 5. Even people keep them to 1 is to 10, 1 is to 7, and sometimes vice versa. People also do, like people take more of vector and less of insert. But generally, in my experience also, most of the ligation reactions works well in 1 is to 3, 1 is to 2, or even at 1. Sometimes you will get at 1 is to 1 ratio also. So people, it's a hit and trial method when you do the ligation reaction initially, and you have to try a lot of like you have to try at least 3 4 molar ratios to get your ligation uh, work. So the following example will illustrates the calculation of amount of insert required at a specific molar ratio of vector is to insert. So you have to careful, you have to be like vigilant here. So how much nanogram of vector you are going to take, how you will find how much nanogram of vector. So let's suppose uh, you, you purified a plasmid. Okay, you purified a intact plasmid, and then you did a restriction digestion, and after restriction digestion then you again did some purification steps, and you calculate, you went to nanodrop or a spectrophotometer, and you calculate that how much nanogram of DNA is there in 1 microliter. So let's suppose in my experiment, so when I took reading, I found that for vector, when I went to that, and you know how to know that how much nanogram of vector is there in per microliter, and how much nanogram of PCA product is there in per microliter. You are very used to it, and you were doing this kind of experiment in your this instrumentation lab. Those students who are not able to get it, that's why I'm telling you that there is a machine called spectrophotometer in your instrumentation lab, and you go there, you fix at 280, the wavelength at 2 so sorry, at 260, and you calculate that how much nanogram of DNA is there in 1 microliter. So let's suppose in my experiment I went to instrumentation lab, and I found that 100 nanogram of DNA is vector plasmid is there in 1 microliter. So in 1 microliter I have 100 nanogram. Similarly for my insert, the insert the required PCR product, or the required fragment that you want to ligate with the vector. So to give some previous link, that you did a PCR, after PCR you digested that PCR product with the same enzyme that to which you digested the vector, and then after, once the digestion is complete of your PCR product, then you PCR purify your product, and then again you calculate the amount of insert in per microliter. So let's suppose I found that it is 50 nanogram of per microliter. So 50, So the concentration for my PCR product is 50 nanogram per microliter, and for my vector it is 100 nanogram per microliter. Now carefully look into this formula. So how much nanogram of vector into kb size of insert? So how much is the length of your insert? Let's suppose the PCR product that you amplified and you want to insert inside vector with vector. Let's suppose it's 500 base pairs. Let's suppose it's 500 base pair and it's written in kb. So it will be 0.5 kb. It is like 0.5 kb. And kb size of vector, let's suppose my vector is 3000 base pairs, so I will write 3 kb of vector into molar amount of insert in and the molar amount of vector. Let's suppose you are taking 1:3 molar ratio of vector and insert. In this case 1 is vector and 3 is insert. What you have to write in formula is molar amount of insert is to molar amount of vector. So 3 will be your insert, and 1 will be your vector. That will be the nanogram of insert which will be required for this molar ratio. So because just I had said that for ligation you have to do lot of hit and trial, and you set up various ligation reactions at 1:1, 1:2, 1:3 till 1:5. Or even some people go till 1:10. So the question is that how you are going to decide that how much nanogram of insert you will take to make the molar ratio 1:1, 1:2, 1:5, or 1:3, or 1:10. So we are calculating that how much nanogram of insert you are going to take. So let's suppose I fix that I'm going to take 100 nanogram of vector. I'm going to take 100. Generally in ligation reaction people keep 100 nanogram of vector or 50 nano or 150 nanogram of vector. So how much nanogram of vector is 100 nanogram of vector. Similarly you have to find that how much nanogram of insert you are going to take. It's not that if my vector is 100 nanogram and nanogram of I'm taking 100 nanogram of vector and I want to set up 1:1 ratio. So for the vector is 100 nanogram, then insert will be 100 nanogram. No, it is not like this. It depends upon the mass. It depends upon the size of insert. So to consider all these factors, we use this formula, because this formula consider what you can see is that it is considering how much kb or how much is like what is the size of your insert, what is the size of your vector. So on the basis of these factors we calculate that how much nanogram of insert you are going you are going to take for 1:1 or for 1:3 ratio. So here 1 is vector and 3 is insert. So let's it will be more clear through this example. So how much 500 base pair insert DNA needs to be added to 100 nanogram of 3 kb vector in ligation reaction which is desired for vector into insert is 1:3. It's 1:3. So 1 part of vector and 3 part of insert. I'm repeating it again and again because when you will write them in formula, it will be like the molar amount of insert is to molar amount of vector. So it will be 3:1 there in formula. So we know that we are fixing that vector, that we are going to take 100 nanogram of vector for a ligation reaction. So it will be fixed 100 nanogram. And the size of your PCR product was 500 base pair. So in kb it will be 0.5 kb. Then you will and then divide by length of your vector, which was the size of your vector it is 3 kb of your vector, into molar ratios of insert. This is insert and vector. So it will come nearly to 50 nanogram of insert. When you will take 50 nanogram of insert, then it will become 1:3 ratio. So suppose we did not apply this formula. So initially I said that I will fix my vector to 100 nanogram. So by this it will be like I have to take 300 nanogram of insert. but what we are getting, it is 500 nanogram, because the formula is considering both. It's considering the size of insert and size of vector. So it's not a direct thing. Like if vector is 100 or 1, then for 1:3 molar ratio, so I took vector 100 nanogram, so PCR product will be 300 nanogram. No, it will be, it depends upon the size of PCR product and size of vector. So for 1:3, what you are getting when you put all these value is 50 nanogram. So you have, so I guess this is clear. And what I want to add here is that why people take more of insert. Like you will see that people are take what we are writing is 1:3, 1:5, or till 1:10. That 1:3 is 3 part of insert, 1:5 is 5 part of insert, 1:10 is 10 part of insert. So why people generally take more of insert? Because in general the size of insert is less. Size of insert is less. So to increase the chance of collision of insert and vector inside in a ligation reaction, we keep more of insert. So if because insert is small, so the chances of collision will become more if the concentration of insert is more in the is more in ligation reaction. So it's a journal explanation for this, but there are papers in 1980s which suggest that it all depends how pure is your samples are, how pure, like how much free it is of DNAs and all. It do not depend that it is not necessary to take more of insert, then only it will work. So people have their own fundas in this, but in my view what I have also used is like I have kept in more of insert and it has worked very well. So it depends. And again I will repeat that it's a hit and trial method. So whenever you are going to put ligation reactions in future in your lab as your lab work, you have to try a lot of reactions, this ratios here. So let's suppose I'm going to take a vague example here to take you in a virtual, that how we set up a ligation. You have set up a ligation in lab. So let's suppose so I am taking T4 ligase. I am taking T4 ligase as my enzyme. So we know that enzyme need what? Buffer. So the concentration of buffer is 10x. So the concentration of T4 ligase buffer is 10x. In total, I want to set up a reaction of 10 microliter. A 10 microliter ligation I want to set up. So okay. So the buffer is 10x and I want to keep it 1x. So it will be, the working will be 1 microliter because it's 10 microliter total reaction. So 1 microliter of what? Buffer. Okay. Then you have to keep a vector which is digested vector. And for this, how much? So and you wanted to put it as 100 nanogram. So 100 nanogram of vector, how you will calculate that? How much microliter of vector I will add, then it will be 100 nanogram. So because you remember that we fixed the vector to 100 nanogram. So and for that's why for this we did what? We took reading, and through reading we found that in 1 microliter we have 100 nanogram of concentration. So it's a direct thing. So vector will be 1 microliter. Similarly for insert, we calculated that we need what? 50 nanogram of insert. And through our UV reading, through our nanodrop reading at 260, we found that if after PCR purification of a digested PCR product, it is 50 nanogram per microliter. So and what we required, it's 50 nanogram. So it's very direct. So I will write 1 microliter of this insert, and then I will include enzyme, and then I will add what? Water to make. So let's suppose I added 0.5 microliter of enzyme. So it will be 3.5 microliter and rest will be 6.5 microliter will be water, and it will make a total reaction of 10. Total will be 10 microliter. So it can be, so insert here it can be 100 nanogram. So when you calculate it, it can be 100 nanogram per microliter. 100 nanogram per microliter. But for what you calculated is what required is, let's suppose I'm taking a different scenario. What you calculated for 1:3 is 50 nanogram. So then insert will be what? So in 1 microliter it has 100 nanograms. You want to keep 50 nanograms, so it will be 0.5 nanogram, 0.5 microliter of insert in case when this concentration for insert comes to be 100 nanogram per microliter. But initially what I took the example is 50 nanogram per microliter, so I want to keep it 50 nanogram, so I directly took 1 microliter. So you know how to do this calculation. So you can visit this biomath calculator, which is designed by a company called Promega, and you have to directly put the values of how much nanogram of vector is there, what molar ratios you are for what molar ratio you want to calculate the nanogram of insert. So it's a direct it's software, and you can calculate how much nanogram of insert will be required for 1:3 reaction. So this has been taken from Promega website, and this biomath calculator is also developed by this Promega company. And this is the formula that you have just seen there. So it's the insert mass in nanogram is the nanogram of vector. In our case it was 100, so we took 100 nanogram of vector. Kb, it was 500 base pair, so it will be 0.5 kb is the length of your insert. And kb size of your vector, in our example it was 3 kb or 300 base pairs, so I will write 3 kb. And molar ratio of insert is to vector, so it was 3:1. Similarly, you can keep changing them to 2:1 or 1:1. So it will be interesting to find that how much nanogram of DNA comes. So it was 50, so I guess it nearly for it will come like near 25, or for 1:1 it will come for around 12 or 13. So you can calculate it. But I also used one other software which was which is NEB, New England Biolabs, and so they also have their own this calculator where you have to just add the insert DNA length. So in our case it was 0.5, vector DNA length, so it was 3, and how much vector we were taking, it was 100 nanogram. So why we are taking 100 nanogram of vector, I'm repeating that in general we generally for a reaction for ligation reaction we keep it as 100 or 150 nanogram of plasmid. So that's why we took 100 nanogram of plasmid here. And what you can, as soon as you're going to add this, you will find another table on your right side that what is the required insert for 1:1. So 1 of vector and 1 of insert, so it will be 16.6 nanogram. For 2:1 it will be, so it will be 33.33, not 25, so it will be 33.33. I didn't calculate it there, so it will be 33.33 nanogram. So 2 of insert, 1 of vector. So they are using insert is to vector ratio. For 3:1 it will be 50 nanogram. So this was your answer when you calculated for 1:3 or 1:3. In 1:3 it was 3 part of insert, so I am here writing 3:1 where 3 part is of insert and 1 part of your vector. Similarly you can go on, and the formula is very straight what they are using, and it is same, but I like this formula because what you have to just take is that desired insert molar desired insert vector molar ratio that we need is 3:1. So I want to keep 3 of insert and 1 of vector into mass of your vector. It was 100 nanogram, and then you have to, so mass was 100 nanogram, here it was 100 nanogram, and then the ratio of insert to vector length. So insert was 0.5 and then 3. So you can calculate what will be the answer here. So it's a very direct formula, and it is from NEB biocalculator. So I guess most of your doubts are clear. If you have any doubt, you can write to me. And in next audio PPT, as discussed with Urmi ma'am told me to discuss about our method of for COVID-19 testing, our one-step real-time PCR method for testing COVID-19, and it will be good learning experience for you as well, because the motto is that you people also learn that how to develop these diagnostic tool for these kind of diseases. So I thank Urmi ma'am for giving me this opportunity to make audio PPT on this. I will make it shortly. I'm waiting for some kind of approval, and once it is done, I will make audio PPT on this. Thank you.